All right, so everyone has their microscopes out. And so how many of you have the letter E? Raise your hand. Letter E. Okay, so what I want you to do is to look in the microscope and tell me what it is that you see. Does the letter E look normal?
No.
No, it doesn't. What does it look like?
Upside down.
It's upside down. Okay, so the term that we use to say upside down, we say that it's inverted. Okay? So the question that I'm going to answer is, why is the letter E inverted? Why is it that you're looking at it through this microscope and it's upside down? Okay? But in order to answer this question, we have to understand, I'm going to show you what this schematic is, what I'm trying to show here. So this top part right here, this is going to be the ocular lens. Okay, so let me write that down. So number one, this is the ocular lens. So this is what you're looking through. So let me draw eyeball here. This is the pupil, colored part of the eye here. This is the iris. We got a little eyebrow, and then we can even draw a little nose there. Okay. So this is looking through the ocular lens. So that's number one. Number two, what would this be called? The objective. Yeah, so this is the objective lens. Okay, so one of the defining features of these lenses, both of these lenses are known as convex or converging lenses. Okay, and you'll see why this is the case. All right, so the next thing that I have here, number three, so this is the condenser. And what is the function of the condenser? What does it do? Exactly, it concentrates the light, which is what I'm showing here. This is the light, this little light bulb, right? This is the light source. And so number four, this is what controls the amount of light that's going to pass through this condenser. And so what is this called? The iris diaphragm. So you have the iris diaphragm. All right. So what I want to show you is the similarities between the microscope and then the eyeball itself. Okay? So here on this schematic, coming from this light source, so light travels in, they're called parallel rays. Okay, so they're traveling in this direction. So it'll pass here through the condenser, okay, and a phenomenon happens. This phenomenon is known as refraction. So you have refraction and then a phenomenon known as reflection. Okay, so if I'm standing in a mirror, what am I looking at? Am I looking at a refraction or a reflection of myself?
Reflection.
I'm looking at a reflection of myself. And so if I draw a plane here, okay, when the light ray travels down, is it going to go here or is it going to bounce back up? Yeah, it's going to bounce back up, right? So it goes up like this. And then this here is the plane of symmetry. So that's what reflection is, when it bounces off. Refraction is whenever it passes through the second medium. Okay, so this is what a medium is. So the medium in this case would be the lens of the condenser. So the condenser is also a convex lens. Okay, so what I'm going to represent, so this will be N1 and this will be N2. Okay, and what this stands for is the index of refraction. So let me write this down here. So N is equal to C over V. So what does that mean? So C is the speed of light and V is the velocity that the light ray is traveling. Can anything travel faster than the speed of light? No. Not even like Flash, right? The superhero, right? Nothing can travel faster than the speed of light. And so if you look at this number, it's just a ratio. So if this number is, so the speed of light, so it's always, this number is always going to be lower compared to this one, right? Because it's going to be traveling slower than the speed of light. So then this number in the index of refraction is always going to be greater than 1. So for instance, the index of refraction for the cornea, which is this part here of the eye, n is roughly equal to 1.4. Make sense? Yeah? So instead of reflection happening where the light ray bounces off, what it does is it'll bend here towards the we call this the normal. So let me erase this. So that was reflection, and this here is refraction. So you see how the light ray, it's bent? So let me show you what that looks like. So here, so this is air, and this is another medium, right? In this case, it's water. And so you see here, you look at the glass of water, see how the pencil is here? Does it look in a straight line? No, it's bent, right? Because refraction is happening. Okay. So let's go back to the drawing board. So once this parallel light ray is going to travel through this condenser, the light ray will go down. So it goes down this way, and then it goes here through this lens. And then the same thing is going to happen here. So it'll go here, it'll cross here, and then it'll go like this. And so the object, so what would the object be in this case? The letter E. Right, this is what we're looking at. So this is why we call this the objective lens, because we're looking at an object here. So when we say the definition of the condenser, what was the definition of it again? It concentrates the light. So you see how it forms this cone? Look at the intensity here, right? Because the light rays are converging here at this point, and they're illuminating this object. And with this object, this is how we're able to form what we call an image. Okay? So once we reach here to the objective lens, now the light rays are going to converge. And when they converge, that's when we form what we know as a real image. Okay? So what I'm going to draw, the real image is going to be inverted, right? Because that's the question that we're answering, right? Why is the letter E inverted? It's because the light is going to refract here at this convex lens, or this converging lens, and once it converges, the image is formed upside, it's inverted. So let's draw that. So this goes down, and then the light ray continues. So it goes there, and then this one's going to continue straight along this path. And so the image that's formed is right here, the point at which the light rays converge. So we'll call this number 5. So number 5, that is our real, we call it real inverted image. And so once the light rays converge, they're going to continue, refraction is going to happen again, right? Because it happened here once at the objective lens, now it's going to happen at the ocular lens. So once it passes through this medium, it'll go up to the eyeball. It'll go up to the eyeball. See, the light ray is refracting. And so for the real image, the definition of it, another part of it, so the real image is formed. So the image is formed on the opposite side of the light source, which is here. This is our light source. So here is the real image. This is the light source. So the image forms on the opposite side of the light source. But now we're going to discuss what a virtual image is. So the eye is able to trace these light rays back. So the light rays will go like this. This. And the virtual image is what forms here. So we'll call this number 6. So number 6, this is our virtual. Is this image inverted still? Yeah, it's still inverted. So it's a virtual inverted image because it's just magnifying this image that's here. So the real image is formed within the tube of the microscope. Okay? So our virtual inverted image, and where is this image formed? Is it on the same side as the light source, or is it on the opposite side of the light source? The same side. So do you see the difference here between the two? So the image is formed on the same side as the light source. And are light rays converging at this point? Like this? No, they're not. So with the virtual image, the eyes trace back the refracted light. All right, so they're tracing it back because this image isn't real. It appears as if it's, right where the stage is, but it's not actually there. It's virtual. Okay. So any questions regarding this of why the letter E is inverted in the microscope? No. So once again, what happens? The light source, the parallel rays will travel through the condenser. They will converge. They converge here. They get on the objective lens. Once they get to the objective lens, refraction happens. They converge at this point. They form the real image. So the real image, so what is the real image formed by? The objective lens. So the objective lens is responsible for forming the real image. This is very important right here. The objective lens is what forms the real image, and the ocular lens is what forms the virtual image. Okay. So now I want to show you the similarity between the microscope and the eye. So remember, like I was saying earlier, the cornea here, this is the part where you touch on your eye when you're putting your contact on. So when you put your contact on, so is refraction happening here at the cornea? Yeah, because it's a different medium, right? It's going to a different, it has a different index of refraction. So the light ray will refract. And then what controls the pupil size? Whether the pupil is dilated or whether it's constricted. So the iris, so the colored part of your eye, that's the part that's going to constrict or dilate. So if the pupil is dilated, is more light coming through or less light? Yeah, more light is coming through. But if it's constricted, not as much light is passing through. So then we could say, right, that the condenser is functionally similar the condenser is functioning similar to the cornea. And then the iris of the eye is functioning similar to the iris diaphragm, right? The name is pretty much the same. You just add the diaphragm in there. Okay. All right. So that's it for the compound microscope. All right. So now we need to talk about a couple other different concepts for the microscope. So one is, I'll just leave this up here. So one is the field of view, and two is the depth of field. But before I get into this, we also need to calculate the total magnification. So the total magnification is going to be equal to what whenever we're in, let's say, low power. What is the total magnification? 100x. We're just multiplying the ocular lens times the objective lens. So the ocular lens, the magnification is not going to change. The only thing that's going to change is the objective. So 400x. That's the total magnification when we're in low power or high power. Okay, so back to these two concepts here. So the field of view, the first thing I want to say for the field of view, so I'm going to write FOV. So let me put this more towards the center. So as you increase the magnification, there's going to be a decrease in the field of view. When I say increased magnification, what do I mean? Going from low power to high power. That's what I say, increase the magnification. So this is known as an inverse relationship. And so what is the field of view? So if you have the letter E, what I want you to do next is to switch from low power to high power. So when you switch from low power to high power, the image should be mainly focused. Okay, you're not going to have to touch the coarse knob adjustment. The only thing you have to touch is the fine coarse, the small knob, to improve the image resolution. So moving from low power to high power, and because the images remains focused, the term we use to describe that is known as parfocal. So when you switch from low power to high power, the image is mainly focused. Okay, so now tell me what you see for the letter E. Can you see all of the letter E? No, you can't. So I'm just going to draw the regular E, not inverted, just so to simplify. But when you switch to high power, you're zooming in on this particular region of the letter E. So what it'll look like, it'll look something like that, because you're not able to look at the entire letter itself. Make sense? Yeah? Okay. So that was the field of view. You're zooming in on a particular region, and so when you zoom in, as you increase the magnification, there's a decrease in the field of view, what you're able to see. It's kind of like you use your iPhone, and then you can kind of like scroll like this, and then you're like zooming in on whatever particular object it is that you're interested in, that you want to take a picture of. So it's a similar concept here. Okay. So now, that was one. So number two, the depth of field. So when you're in low power, so this was for letter E, and then this is for the threads. So for the threads, there are 3 different colors. You have red, yellow, and blue. So when you switch from low power to high power, the first thing I want you to do is to look at this part right here, which is known as the aperture. So is the aperture the same size in low power and high power? No, the aperture is smaller whenever you're in high power. So what that means is that once you're in high power, you're typically going to have to increase the light intensity. You have to increase the light intensity because it's a smaller, the aperture is smaller, so not as much light is able to pass through. So you have to turn the light up a little bit. Okay, so that's a concept. And then also, you'll also notice that, so the distance between the objective lens and then your slide, it's going to be a lot smaller between the objective lens and then the slide itself. So the distance between the two, that's what's known as the working distance. This is why you do not use the coarse adjustment in high power. Because if it's too close, what's going to happen? You're going to crack that. Yeah, you're going to crack this, crack that slide. Okay, so now let's go into depth of field. So with depth of field, I already talked about the working distance, but for each particular objective lens, there is a perfect plane of focus. For each objective lens, there's a perfect plane of focus, meaning that you'll get a perfect image. So if you look at the image whenever you're in low power, so if you have the threads, go ahead and look at that now. And what you'll notice is that all 3 of these, the red, yellow, and the blue, all of them are focused. They're all focused. But when you switch to high power, you can only focus on one of them at a time. So only the red will be clear. So when the image is clear, we know that we describe that term as resolution. Resolution means image clarity. So just to kind of go back here, so the condenser, not only does it concentrates the light, but it increases the image resolution. Because it's concentrating that light, but it's also improving the image at the same time, okay? But, so the image is clear, you can only focus on one of them at a time. And so it's the similar case as far as the relationship. So as you increase the magnification, there's going to be a decrease in the depth of field. And so what this microscope does, what it allows us to do, it allows us to focus on one particular thing at a time and determine the order that they're in. Okay. All right. So any questions regarding these concepts, and if you have anything on the compound microscope as well? No? All right. All right, so that's it for this lecture.